Okay, here's a question for you. Maybe sounds a bit strange at first. Have you ever, held a really hot cup of coffee and just wondered, does this actually weigh more now than it did when it was cold? I mean, your gut feeling, right? Your everyday experience just shouts, no, of course not. Weight is weight. But what if I told you that the fundamental laws of physics, the deep down rules of the universe, kind of whisper something different? That adding energy, like heat, does actually subtly increase an object's mass. And therefore, yeah, it's weight. It flips things on their head, doesn't it? And look, this isn't just a weird bit of trivia. It's really a journey. It takes us from, Isaac Newton's world, which seemed so neat and predictable, all the way to Albert Einstein and his, frankly, mind-bending ideas about reality. We're basically going to peel back some layers today. Get a look at something pretty profound about how stuff actually works. Now, I'll give you the spoiler up front. The amount of extra weight, it's incredibly, unbelievably tiny. Like, you'll never notice it making your coffee, ever. And yet, the fact that it exists at all, that's a cornerstone of modern physics. It tells us so much about the universe, from the tiniest specks to the biggest galaxies. So, yeah, get ready to maybe question that intuition a bit. Okay, so, to really dig into this, we probably need to get our terms straight first, make sure we're all using the same language, like a quick toolkit check before we dive in.
Exactly. Precision is key here. Let's start with mass. So mass, fundamentally, it's about the amount of stuff in an object. But maybe more importantly, it's a measure of its inertia.
Inertia, like how hard it is to push something.
Precisely. Think about pushing a bowling ball versus a tennis ball.
Yeah.
The bowling ball has way more mass, right? It resists being moved much more. It's harder to start, harder to stop. And that property, mass, it's intrinsic. It doesn't change whether you're on Earth, the moon, or floating out in space. Your mass is your mass. Now, weight, people mix these up all the time, but weight is different. Weight is actually a force.
A force.
Yeah, specifically, it's the force of gravity pulling on that mass. So your mass stays the same, like we said, but your weight, that definitely changes depending on the gravity. On the moon, gravity's weaker, about 1/6 of Earth's. So you'd weigh much less, even though the amount of your mass hasn't changed at all.
Okay. So when we ask if hot coffee weighs more, we're really asking two things. Does the heat add mass, and does that extra mass mean gravity pulls on it harder?
Exactly. You got it. They're linked. So next up, temperature. What is temperature, really? It's a measure of the average kinetic energy, the movement energy of all the tiny atoms and molecules inside an object. When you heat something up, you're essentially making those particles jiggle and vibrate faster. More energy.
So hot things have particles buzzing around like crazy, and cold things are calmer.
Pretty much.
Yeah.
That collective internal jiggling, all that motion energy inside the object, that's what we call its internal energy, or you'll often hear it called thermal energy. It's energy stored inside due to that microscopic movement. And then there's heat. Heat isn't something an object has like temperature or mass. Heat is the transfer of that thermal energy. As it flows from a hotter thing to a colder thing.
So cold isn't really a thing in itself, it's just less thermal energy.
Exactly. It's just the absence of a lot of that internal energetic jiggling.
Okay, wow. So mass is the stuff, or inertia. Weight is gravity's pull on that stuff. Temperature is the jiggle speed. And heat is the transfer of that jiggle. Got it. Right, so with those tools in our belt, let's tackle this coffee cup question. And maybe the best way is to, rewind time a bit, go back to when the universe seemed a lot simpler.
Yeah, let's jump back to the 19th century. This is the era of classical physics, Newton's territory. The view then was kind of like the universe was this giant predictable machine, like clockwork. Everything followed these really clear, distinct laws. It all seemed very orderly.
And a really core idea back then, wasn't it, was that matter and energy were just totally separate things, like two different categories.
Absolutely fundamental assumption. Matter had mass, and you couldn't create or destroy it. That was a law of conservation of mass. Energy could change forms, chemical to heat, whatever, but the total amount of energy was also conserved.
So there were parallel tracks,
Right.
never crossing.
Exactly. Two immutable pillars of reality, completely unrelated in any fundamental way. So in that classical world, what happened when you heated something? Simple. You just added energy. Its internal thermal energy went up. The atoms vibrated more. That's why things expand when heated. The atoms need more room to jiggle. But, and this is the crucial part according to classical physics, adding that energy had absolutely zero effect on the object's mass. The amount of stuff stayed exactly the same.
So adding paint to a car, you said, changes a property, but not the car's actual substance or weight.
Perfect analogy.
Yeah.
It changed how it behaved, maybe its temperature or size slightly, but not its fundamental mass.
But hang on, didn't some meticulous scientists back then with really sensitive scales sometimes notice tiny changes, like a hot object seeming a bit lighter sometimes.
That's a great point. Yes, they did observe things like that, but they had explanations that fit neatly within the classical framework. Nothing to do with mass changing. The main explanation was usually air currents.
Mm-hmm.
A hot object heats the air right next to it,
Yeah.
light air rises, right? So that rising air creates a little upward push, a buoyant force on the object. On a very sensitive scale, that upward nudge makes the object appear to weigh less.
So it was seen as an illusion, like a trick of the experimental setup.
Exactly, an experimental artifact. A nuisance to be accounted for, not a sign of new physics. He wasn't changing the object's actual weight, just interfering with the measurement.
And we have to remember, this classical view worked so well for so long. It gave us steam engines, let us predict planetary motion with incredible accuracy. It built the modern world in many ways. That separation of mass and energy, it wasn't just an idea, it was bedrock. It worked for everything they could measure. So the idea that heating your coffee could add mass, honestly, it would have sounded like utter nonsense back then. But then the calendar flips to the 20th century, and along comes Albert Einstein. And everything changes, specifically 1905 and this little equation, E-mc/s/e italicois. Talk about a seismic shift.
Oh, absolutely seismic. Probably the biggest shift in physics ever. Because EMC just completely shattered that old idea of mass and energy being separate. What it tells us, in its elegant way, is that mass is a form of energy, and energy has mass. They're not two things. They're like two sides of the same coin. Two different ways the same fundamental stuff can show up.
A complete break then, a new paradigm.
Totally. And fundamentally changed everything.
And this is where we get things like nuclear power, right? Converting a tiny bit of mass into a huge amount of energy.
Exactly. Nuclear reactors, atomic bombs. Those are dramatic examples of M converting to E. M disappearing, energy appearing. But crucially, the equation works the other way too. Energy can be converted into mass. E can become M. So if you add any kind of energy to an object, could be kinetic energy by making it move faster, could be potential energy by lifting it up, or, and here's our connection, thermal energy by heating it. You are, according to EMC, also adding a tiny amount of mass.
Wow. Okay, so back to the coffee.
Back to the coffee. When you heat it, you increase its internal thermal energy. Those molecules are jiggling faster. That added energy contributes directly to the total mass of the coffee. So the answer is yes. A hot object is fundamentally, infinitesimally more massive than it was when it was cold. And because it's more massive.
It weighs more, gravity pulls on it just that tiny bit harder.
Precisely.
But the reason it's so tiny is that Clough factor in the equation, right? The speed of light squared. That number is enormous.
Absolutely enormous, which makes you get, for a given E, incredibly small in everyday situations. Think of it this way. An object's total mass isn't just the sum of its particles, like protons and neutrons, added up. It's also the energy binding them together, the energy of their motion. All of that contributes. So when you heat the coffee, that thermal energy becomes part of its total mass energy package. It gets folded into the object's very being, you could say, making it slightly heavier. And then Einstein didn't stop there. About 10 years later, he gave us general relativity, his theory of gravity.
Right, which wasn't just about how gravity works, but why.
Exactly. Newton told us what gravity did. Things attract each other. Einstein explained how it worked. He said gravity isn't really a force pulling things together across empty space. Instead, he said that mass and energy actually warp or curve the fabric of space-time itself. You know the analogy, right? Like putting a bowling ball on a rubber sheet.
Yeah, it creates a dip, and a marble rolling nearby curves towards it.
That's the idea. Objects just follow the straightest possible path through this curved space-time. What we feel as gravity is just us moving along those curves. Now here's the kicker from general relativity for our question. It says that it's not just mass that curves space-time, all forms of energy do too, and that explicitly includes thermal energy.
Wait, really? So the heat energy itself contributes to the gravitational warping?
Yes, directly. So when you heat an object, the added thermal energy does two things, according to Einstein. One, via ECMC fascia, it increases the object's mass. Two, via general relativity, that energy itself adds to the object's ability to curve space-time around it. It makes the object's gravitational influence just that little bit stronger, independent of the mass increase, though related.
So it's like a double effect, almost.
You think of it that way, it creates this beautiful unified picture. Adding heat adds mass energy, and that mass energy is what generates gravity by warping space-time. Energy in all its forms is a source of gravity. The warmth from your radiator, technically, is creating its own tiny gravitational field. It's an amazing thought.
Okay, my mind is officially a little bit bent, so yes, the coffee weighs more. But just how much more are we talking about? Like, can we put a number on this?
We can definitely put a number on it.
Yeah.
And this is where you really see why we never notice it. Let's take a standard example. 1 kilogram of water. That's about a liter. Imagine heating that 1 kilogram of water from basically freezing 0 degrees Celsius up to boiling 100 degrees Celsius. That takes a fair bit of energy. Around 420,000 joules, actually.
Okay, 420,000 joules. And how much mass is that?
Right, now we use Einstein's equation. M equals EC quart. E is 420,000. And C, the speed of light, is huge, about 300 million meters per second. Squaring, that gives you 90 quadrillion. That's 9 with 16 zeros. So you divide 420,000 by 90 quadrillion.
And you get, I'm guessing it's small.
Extremely small. You get about 0.00000000007 kilograms.
0.8047 kilograms.
Yep. Or, to put it in more manageable units, that's 4.7 nanograms.
Nanograms. Okay, I need some context for nanograms. How small is that?
Right. Think about a single grain of ordinary sand. That weighs roughly 1 million nanograms.
1 million, okay.
Or maybe a human eyelash. A single eyelash weighs maybe a few thousand nanograms.
Whoa, okay. So the mass we added to a whole kilogram of water by boiling it is less than 1/100,000th of the weight of an eyelash.
Exactly.
Yeah.
It's fantastically small, like comparing one blade of grass to a giant park.
It's almost comical, really. My steaming hot latte is heavier, but by an amount so small, it's basically imaginary in practical terms.
And that's why nobody ever noticed this effect before Einstein, and why we can't measure it directly on everyday objects. Our best scales just aren't anywhere near sensitive enough. Those effects classical physicists worried about. Air currents, vibrations, they cause apparent weight changes millions, even billions of times larger than this relativistic increase. They completely swamp it.
So for all practical purposes in the kitchen, the classical guys were right. The weight doesn't change.
Practically speaking, yes. The change is effectively zero for anything we can actually weigh or experience directly. But fundamentally, at the deepest level of reality, they were wrong. The mass does change. It's not zero. And knowing that points us to how the universe really works.
Okay, so this leads to a really obvious question, I think maybe for you listening too. If this change is so ridiculously tiny that we can't even measure it on a coffee cup, how are scientists so absolutely sure it's real? How can we know?
That's a perfectly fair question. And the answer is, we don't know it from directly weighing hot coffee, obviously. We know it because the principle behind it, EMC panic, has been confirmed with incredible accuracy in other areas where the energies involved are just vastly larger.
Like where?
Think about nuclear physics and particle physics. In particle accelerators, like the Large Hadron Collider at CERN, they slam tiny subatomic particles together at almost the speed of light. The energy involved in those collisions is immense. And what happens? New particles are created. Literally, energy is converted into mass, into new particles that weren't there before. And physicists can measure the masses of these new particles, and they match exactly what EMC panic predicts should be created from the collision energy. It's not a tiny effect there. It's the whole point.
So we see energy turning into mass very directly in those extreme conditions.
Very directly, and with amazing precision.
What about the other way around? Mass into energy. We talked about nuclear power.
Right. Nuclear power plants are another perfect example. When uranium undergoes fission, the resulting particles actually have slightly less mass combined than the original uranium atom. That tiny bit of missing mass hasn't vanished. It's been converted into a huge amount of energy, the heat that drives the power plant. And again, the amount of energy released matches the measured mass difference perfectly, according to EMC match.
So the theory is tested and proven in these extreme cases, both E into M and M into E, with incredible accuracy.
Exactly. Our confidence comes from the overwhelming, consistent success of relativity theory, both special relativity and general relativity, in every single domain where we've been able to test it. It forms a single coherent picture of how mass, energy, space, and time are interconnected. So if the principle holds true for nuclear bombs and particle accelerators,
It must logically hold true for the thermal energy in a hot cup of tea, even if the effect there is too small for us to isolate and measure directly.
precisely. The underlying physical law is the same. It's real, even if it's hidden from our everyday senses and instruments. It's about the consistency and predictive power of the entire theory.
Okay, that makes sense. So, if this effect is basically negligible for us here on Earth in our daily lives, why should we care? Apart from it being a cool, mind-bending fact, where does the weight of heat actually become significant? Where does it matter?
Now we get to the cosmic scale.
Yeah.
And out there, this effect is anything but negligible. Think about stars, like our own sun.
Okay. big ball of hot gas.
A very big ball of very hot gas. It's essentially a giant nuclear furnace. Down in its core, the pressure and temperature are immense millions of degrees, and it's constantly undergoing nuclear fusion. Mostly hydrogen atoms are fusing together to form helium, and in that fusion process, a small fraction of the mass of the hydrogen doesn't end up in the helium. It gets converted directly into energy, light, and heat, according to E equals C1.
That's what makes the sun shine, right?
That's exactly what makes it shine. And here's the direct consequence. The sun is constantly radiating that energy out into space. And since that energy has mass,
The sun is losing mass.
constantly, every single second, our sun converts about 4 million tons of its mass into pure energy that streams away into space.
4 million tons every second.
Wow. That's EMC sub-shores happening on a colossal scale, right there above our heads. The heat and light hitting Earth literally used to be part of the sun's mass. And there's more. That immense thermal energy inside the star, the sheer heat and pressure generated by fusion, it plays a critical role in the star's structure and stability.
How so?
Well, we know from general relativity that energy creates gravity. So all that thermal energy inside the star contributes to its own gravitational pull. But maybe more importantly, the outward pressure generated by that intense heat pushes against gravity's inward crush. That energy is actively helping to hold the star up, preventing it from collapsing under its own weight immediately. When astronomers model how stars live and die, how they evolve over billions of years, they absolutely have to include the mass equivalent of all that internal thermal energy. It's a crucial part of the calculation. For stars, the weight of heat is a huge deal.
So it's not just a footnote for stars, it's fundamental to their existence.
Absolutely.
Yeah.
If we go back even further, think about the very beginning of the universe,
Yeah.
the Big Bang. In those first fractions of a second, the universe wasn't really made of matter as we know it. It was this incredibly hot, incredibly dense soup of pure energy and fundamental particles, practically indistinguishable. The energy density was unimaginable. And in that state, the weight of heat, the gravitational effect of all that energy wasn't just a factor, it was basically everything. It was the immense gravitational influence of that primordial energy soup that drove the initial hyperfast expansion of space-time itself, shaping the entire cosmos, setting the stage for galaxies and stars and eventually us. The weight of energy dominated everything back then.
Wow. Okay, so from a coffee cup to the birth of the universe, that's quite the journey. So let's circle back. That initial question, does a hot cup of coffee weigh more than a cold one? The answer, surprisingly, fundamentally, is yes.
It is. And figuring that out took us through, well, a revolution in physics, didn't it? Redefining mass, energy, gravity, seeing how they're all intertwined. Mass and energy really are just two faces of the same thing, linked by E.C. Cot. More energy means more mass, means more weight. Simple as that, conceptually.
But, and it's a huge but, for everyday life, the actual difference in weight is, well, you said it, fantastically, almost comically small. It's completely undetectable by us or our instruments in normal life. So tiny it gets lost in the noise. Our senses, our kitchen scales, they'll never pick it up. For all practical purposes, the classical view holds.
It does. The real importance of this idea isn't about weighing coffee accurately. It's about what it tells us about the universe's operating system. The fundamental rules. It reveals this elegant, unified reality where the heat you feel, that microscopic jiggling, is fundamentally connected to the gravity holding planets in orbit. It's the same underlying principle.
And that principle, totally insignificant in our mug,
Becomes a dominant shaping force when you scale up to stars or look back to the Big Bang. You simply can't understand astrophysics or cosmology without grasping that energy has mass and creates gravity. It's essential. So maybe the next time you're holding something hot, a cup of tea, a warm plate, whatever, just take a second. Appreciate the hidden physics. That warmth you feel, that atomic vibration. It is adding a tiny, tiny, imperceptible bit of mass to that object. Right there in your hands. You're holding a direct consequence of Einstein's relativity, a tiny echo of a principle that governs everything, from quarks to quasars.
It really makes you think, doesn't it? The universe has all these incredible hidden connections just waiting for us to ask a simple question and then have the curiosity to follow the answer, no matter how strange it seems at first.